So that last f of xy for the previous example was pretty easy, as was the region, because it was a triangle, everything was straight lines. Let's look at a region that's more complicated and a function that's more complicated. So we have our region R, which says xy is such that x squared plus y squared is less than or equal to 4, but y has to be greater than or equal to 0. Now, x squared plus y squared equals 4 is a circle, right? But because y has to be greater than or equal to 0, we're actually only going to look at a semicircle, right? So this is a semicircle of radius 2. Right? So there's our region right here. All right, we've got our region. Lovely. Okay, so now here's where the fun begins. So we have to find our critical points inside the region. I mean, we don't have to do them first. We can find, well, let's just do inside. Inside R. There's no particular order to these. You just kind of do whichever ones you like first, but we'll do the ones inside first. Okay, so remember that this function is really x squared plus y squared minus 2x plus 2 to the 1/2 power. And that'll help us with our derivatives because f sub x would be equal to 1/2 times x squared plus y squared minus 2x plus 2 to the negative 1/2 times the derivative of the interior, which would be 2x minus 2. Okay, so we're going to have to set that equal to 0. And f sub y has to be 0 simultaneously. So that would be 1/2 x squared plus y squared minus 2x plus 2 to the negative 1/2 times the derivative of the interior with respect to y, which would just be 2y. And we can just make Maple do this, right? We can say, hey, Maple, solve these simultaneously for us, please and thank you. And I did that. It's right here. I also have the graph drawn ahead of time, but that's all right. So you can see the region. It's a semicircle, just like I said. And I'll talk more about that later. All right, so there's the derivative. There's the derivative. They've simplified it, of course. And then we wanted to set them both equal to 0 and solve for x, y at the same time, and it comes up with 1, 0. Right, so we'll write that down. All right, so they were solved simultaneously because, of course, if you solve just one of them, you'll get one value, but you need both of them. So solve simultaneously with Maple, and we get 1, 0 as a critical point. Lovely. All right, so now we need the corners. So the corners are easy. There's only 2 corners. So the critical points on the corners are, well, I can make this into a corner, 2, 0 and negative 2, 0. Done with that. Okay. Now, what about the boundaries? Well, that's going to be the hardest part. So the critical points on the boundaries. Now, there are 2 boundaries here. There's the boundary on the bottom, which I'll call A. Right? That's pretty easy because that's just a horizontal line. Right? So that's boundary A. Right? And then there's another boundary, which is boundary B, which goes up and around. And that's going to be trickier because it's a circle. So we'll deal with that in a second. Okay, so let's start with boundary A. Boundary A is y equals 0. So f of x comma 0, which would be f of x, when I put 0 in for y, I'd end up with the square root of x squared minus 2x plus 2, because the y part would disappear, right? Which is x squared minus 2x plus 2 to the 1/2 power. And I'm doing that because I need the derivative. So the derivative of that with respect to x would be 1/2 x squared minus 2x plus 2 to the negative 1/2 times the derivative of the interior, which is 2x minus 2. Ah, that looks familiar. All right, so we want to set this equal to 0 and solve. So just so you know, the 2 would cancel into this, so it would become x minus 1. We've actually already seen this, more or less. So it's over the square root of x squared minus 2x plus 2. And so the only way that's going to happen is if the numerator is equal to 0, because the denominator equals 0 would make it undefined, but that would also be a problem. Actually, I believe this one doesn't actually have any answers if you set it equal to 0, but I can find out with Maple. Yep, sure enough, there are imaginary numbers. So, because remember, critical points can happen where the derivative is 0 or where it's undefined. So this is not going to help us. These are not real numbers. So the derivative equals 0. So let's just say f sub x equals 0 at x equals 1, because the numerator would be equal to 0, and x minus 1 equals 0 makes x equal to 1. It's f sub x is undefined at 1 plus or minus I, which are not real, so we can toss them. They're imaginary numbers, which are great. They're their own thing, but they're not what we're working with. We're working in the real number system here, so we're good. Okay, so now what about boundary B? That's going to be a trickier wicket. Now see, the problem is that we know what a circle looks like. In rectangular form, we learned in pre-calculus a long time ago that x squared plus y squared equals the radius squared. They also gave it to us. It's right here, right? Technically, it's less than or equal to, but we're looking at the boundary, right? The boundary would be equal to. So we know what this circle looks like. This is a circle centered at the origin with radius 2. But the problem is that if you want to put this into the original function, right? Because that's what we've been doing, right? We've been picking values or figuring out the equations and then substituting to get only one variable. Like we only have x here. To make that happen here, you'd have to bring the x squared over, then take the square root of both sides, plus or minus, and yuck, right? It's going to be real ugly that you'd have to put y equals the square root plus or minus the square root of 4 minus x squared into this equation, and then try to find some derivatives. Yuck, yuck, yuck. So what we're going to do is we're going to use parametric form. We learned in pre-calc without realizing it, and then we learned in Calc 2 with realizing it, that the parametric form for an equation, or for a circle like this, is 2 cosine theta to sine theta. Grant you that's rotating counterclockwise, but there's no reason to assume we're not rotating counterclockwise, so it's fine. And that we can do. We could put in these values for x and y into our function, right? So f of x, y could become f of 2 cosine theta to sine theta, which would be the square root of, now it's going to get ugly for a second, but it'll clean up real nice. So 2 cosine theta squared plus 2 sine theta squared, and at that point little bells should be going off in your head, minus 2 times 2 cosine theta plus 2. Now, bells should be going off in your head because this is the Pythagorean identity, right? That's 4, which means the whole thing becomes f of theta is the square root of 6 take away 4 cosine theta. Or if you will, it's 6 minus 4 cosine theta to the 1/2 power. Okay, well, how does that help me? Well, it helps me because the derivatives, right? So I can find the derivative. So the derivative of that would be 1/2 times 6 minus 4 cosine theta to the negative 1/2 times the derivative of the interior, which would be derivative cosine is negative sine. So 4 sine theta, because the negative sine and the negative 4 would cancel. All right, 2 goes into 4 twice, so that makes it 2 sine theta over the square root of 6 minus 4 cosine theta. Now let's remember, this derivative equals 0 when the numerator equals 0. So we want 2 sine of theta equals 0. Theta equals what? Or it could be undefined, right? So this is where f prime would be equal to 0 at these values. F prime of theta would be undefined at 6 minus 4 cosine theta equals 0. Technically it's the square root, but it wouldn't make any difference, right? Okay, so let's look at these values. Where is the sine of theta equal to 0? Right, the sine is equal to 0 at 0, but also over on the other side at pi. And we have to stop there because we're only considering this top piece, right? We're not going to go any further than from 0 to pi. So 0 and pi give us 2 of the values. Well, the theta values, that is. This is actually not going to give us any real numbers because this would mean that the cosine of theta is equal to, bring the 6 over, divided by 4. 6, 4, which is 3 halves, which is greater than 1. So that's not going to be anything that we need to worry about. So not real. It would be an imaginary solution. Okay, so all we have to concentrate on is these theta values and get the critical points out of them. But remember, if theta is 0, right, remember where it came from. 2 cosine of 0 would be 2. 2 sine of 0 would be 0. So this would get us the critical point 2, 0. And pi would get us the critical point negative 2, 0. It's the same ones we already had. We did all of that work to come up with the same values that we already had in the first place. And if you want to see me do it in Maple, here you go. So I said, hey, solve 2 sine theta equals 0 for theta. Now notice it's only giving me the 0 value, which isn't really fair. There's 2 answers here. So this is why you can't trust Maple fully for something like this. It should give you 0 and pi, and it's not. So that's something to keep in mind. And then when I did this one, it said arc cosine of 3 halves, which you might not realize just off the top of your head. That's not real. But if you tell it to do 10 digits, you can see it's 0.962 I. See the I? That's imaginary. So we're done with that one. We don't have to worry about that. So be careful with Maple. Maple's not giving everything here. Right? That's a function of how arc cosine works, really. Okay, so now we just have to make a little table and we'll be all set. So let me draw the table. All right, so we're going to make a table of all our critical points and our f of x, y values. So we have our critical points. We have 1, 0, that was in the interior. We have 2, 0, which is a corner and a boundary one, and negative 2, 0, which was also a corner and a boundary. And then we substitute the values into the function. So we take 1, 0, and we plug it in, and we would get 1. We take 2, 0, and plug it in, and we'd end up with the square root of 2. And negative 2, 0, we would end up with the square root of 10. Which is about 3.16. And this is about 1.4. Let me show you in Maple. And here we go. I have my function named f2. And I told it to evaluate that function at x equals 1, y equals 0. And sure enough, it came up with 1. When I did a 2, 0, it gave me the square root of 2, which is about 1.414. And then negative 2, 0 was the square root of 10, which was about 3.16. So that means that the maximum, the absolute maximum, is actually at negative 2, 0, and the minimum is at 1, 0, 1. And if we look at it on the graph, we can see that this is the case. The maximum happens over on the left. So here, let me orient this so that it's the same orientation, right? So if you look at it from the top, it should look like a semicircle, which it does. And then the highest it ever reaches is over there on the left corner, which is what we thought. And the lowest it ever reaches is in that interior in 1, 0. The graph indeed backs us up. So let me write that down. There. And I circled those because those are the answers that we were looking for. The absolute min happens at 1, 0, 1, and we've proved it. And the absolute max happens at negative 2, 0, square root of 10, and we've proven that as well. And the Maple graph backs us up.